My name is Samane. I consider as a new faculty member at University of Québec at Trois-Rivières. Before that, I was working in industry and in dealing with different kind of project regarding fuel cell and electrolyzer. So very happy to be here with you. So today I'm going to talk about the challenges that we have inside fuel cell and electrolyzer. Basically, Dr. Pole talked about different kind of, hydrogen strategy, different kind of hydrogen production. Today we are going together inside the stack to understand what do we have inside fuel cell or electrolyzer stack. So basically at the end of this presentation, we can somehow know about the challenges that we have and the type of component that we have inside fuel cell and electrolyzer. Okay, so the topic, as you see, is the impact of membrane electrode assembly component on fuel cell and electrolyzer performance and durability. So this is the outline of my presentation. Today I'm going to talk about two important institutes that we have inside UQTR. Then I'm going to talk about fuel cell and electrolyzer, how we are going to classify MEA component. Then we go through the MEA, we talk about the catalyst layer, different kinds of ionomer membrane, and also gas diffusion layer, and we talk about bipolar plate and how we can bring the biomaterial inside these technologies. So as you may know, UQTR is a medium-sized university, but we have two important institutes inside. We have Hydrogen Research Institute, founded back in 1994. It's one of the first institutes in North America to start looking at hydrogen. So if you go, for example, to Fuel Cell Seminar in Long Beach that we have, it is one of the highest, high-level conference in the US. You will see the slide that when they are showing that how the hydrogen start, our institute is there. So we are very proud of that. And we have also I2E3 start looking at biomaterial. So I hired by UQTR 3 years ago in order to join these two institutes together. It means that we want to address how we can bring the bio-based material to energy and battery sector. So thanks to different partners that we have from 3 years ago when I started at UQTR, we make a big group. Now I have 10 PhD, 5 postdoc in my group. As you see, we are working with different companies. We have a project with Accelera, Rio Tinto, NRC. We are working with the mining company. Basically, we are focusing on development of different components, from catalyst layer, ionomer. So the beauty of our research is that we start from scratch. We know how to synthesize the catalyst, how to make the ink, how to apply inside the MEA, how to build the stack, and how we test it. So, and we're so proud of that. I'm sure that you heard a lot about the environmental global warming and a lot of the energy consumption increasing. And so I want to show you this graph that why hydrogen, why we are talking about hydrogen. So hydrogen, as you know, is a clean energy carrier, and if you want to talk about energy density, it's 3 times higher than gasoline, 2 orders of magnitude larger than lithium-ion battery. And also in terms of volumetric density, then we have 4 times the volume of gasoline for the same amount of energy, and order of magnitude larger than lithium-ion battery. In terms of charging, same as gasoline, order of magnitude faster than batteries. So I'm sure if you are in battery and fuel cell field, you get all the time this question, what do you think? Fuel cell or battery? So the answer is the decision already made. For next 5 years, we are focusing on for fuel cell for heavy duty and medium duty and light duty for battery. And until we find I all the time say, until we find the game changing. Because even if we have a perfect fuel cell, very cost effective, good performance, durable fuel cell, we don't have enough hydrogen as a fuel to run all of our fuel cells. So then we need to shift our focus from fuel cell to hydrogen production. So that's why today I'm going to cover fuel cell and electrolyzer together in terms of component. So you see 3 different images for fuel cell stack or fuel cell component. If you just Google it, you will see these kind of images that I'm going to explain for you for the people that they are not in the field. So in the So here we can see the hydrogen fuel cell stack that we have 100, 200 of these cells inside that. So based on the power that we want to get. And then we have the single cell here. So we have bipolar end plate, bipolar plate. Then we have the gas diffusion layer, MEA. MEA is heart of fuel cell or core component of fuel cell, or the place that all the reaction happen. So it's the main part. And then again, the same material on the other side for anode and cathode. So, and if we look at this image, we see that the reaction happens. So it's basically a simple electrochemical reaction happen that we enter the hydrogen to the system. The hydrogen go through anode and is oxidized to proton and electron. And hydrogen, proton pass through the membrane and electron goes through the external circuit. And then from the cathode side, we have electron, hydrogen, and air that we are getting through from the atmosphere. Then we have overall water. So imagine that you have a water, or you imagine you have a car or truck that from exhaust you have a clean water that 100 times cleaner than tap water that you are drinking today. So let's look at comparing PEM fuel cell and electrolyzer. Again, like all electrochemical devices, you have the same component: anode, cathode, electrolyte, different reaction, different reactant. So in fuel cell, we are entering hydrogen, okay? We are entering hydrogen and the oxygen, the byproduct is water. In electrolyzer, we supply water, we split the water, we produce hydrogen and oxygen. It's like a circle together. So I'm sure that you heard about different kind of fuel cell, different kind of electrolyzer. Sometimes we talk about PEM fuel cell, sometimes you see about low temperature fuel cell, or cation-based fuel cell, anion-based fuel cell, all are the same. We have different classification. We can classify our fuel cell based on the temperature that they are working. For example, we can call it high temperature fuel cell or low temperature fuel cell. Same for electrolyzer. We can classify the fuel cell electrolyzer based on the membrane type that we are using, or based on the component that they are transferred. So if we want to talk about the challenges that we have, I can say we have three main challenges overall. So we have cost, durability, and performances. These three challenges are interrelated together. So today we are so lucky because we can address two challenges together. So if you come to us and tell us that, okay, you want a stack, it's cost effective with a good performance, we can build a stack with non-precious metal catalyst. So it performs well, but it's not durable. And if you come to tell us that the cost is not important and you want to have a high performance and high durability, we can put a lot of precious metal there, then we can build a stack with a good performance, a durable stack. So, but the challenge that we have today is that we build a stack that is cost effective with good performance and good durability. Same for fuel cell and electrolyzer. Here in this image, we can see the membrane electrode assembly. In fuel cell and electrolyzer, the majority of the cost of single cell or single stack comes from this part. This is the place that the reaction happens, and we have membrane, that is our electrolyte catalyst layer, and gas diffusion layer. So inside the catalyst layer, as you see, we have our catalyst, then we have a support. The state-of-the-art material that we are using for PEM fuel cell is platinum carbon. And then we have the ionomer, that the role of ionomer is bind this material together and also provide a path for proton conductivity. But the most important part is the pore. So we need to build our catalyst layer in a way that when we supply the reactant, or if we want to remove the reactant, we have enough pore to make it happen. Because if we have a very dense layer, that is impossible when we enter hydrogen, or if you want to remove the water, it becomes impossible for us. So the porosity of the catalyst layer is very important for us. And same for the electrolyzer. Instead of platinum carbon here, inside the electrolyzer, we have iridium-based material. But again, we need to build the same structure of the catalyst layer in order to have a good access for our water when it comes to the reaction. So we can see here two images of our catalyst layer. So this is a platinum carbon bonded with ionomer to form our catalyst layer. And basically catalysts, as you know, it somehow facilitate the reaction for us. And these pores, it provide a network for us for supplying the reactant and also removal of the reactant. And also it provide a network for electronic conductor and also protonic when we have the ionomer. Okay, but our catalyst layer, when we start running and using fuel cell and electrolyzer, we are going through different degradation mode. So it doesn't mean that we can run forever with that catalyst layer. So we have, sometimes we have platinum dissolution, sometimes we have platinum detachment, platinum sintering, carbon corrosion, ionomer decomposition. And we need to address all of these challenges in order to prevent the degradation of our catalyst layer. So basically in our lab, when we produce a catalyst layer or from the company, when we receive the catalyst, then the first step of screening is half-cell study. So we are not going directly to make the MEA to test it inside the fuel cell. We have a half-cell study to test the activity of the catalyst because it's faster and it's very cost-effective, and it gives us the information about, for example, the activity of the catalyst that we produce or receive from industry in compared to the commercial one. So we can somehow simulate the environment of fuel cell and electrolyzer. I put this slide, is very interesting because we found that it's very important when you're using, when you're trying your catalyst, you use the same material from same batch. We got two acid with the same purity with different company, and we end up different result. So that I put it for you for if you're working on catalyst and if you're dealing with different screening, it's very important that you use the same batch of electrolyte to move forward and compare the results together. So through the half cell, you will end up something, the graph like that, the cyclic voltammetry, that you can calculate the hydrogen adsorption and desorption through that and calculate the surface area. The surface area comes from platinum here. But then you can do the BET in order to get the surface area of your carbon-based material as well. And then the other important things that we are doing in our lab is shelf life study. So that also is important because imagine that you're in industry and you're making 2 kilograms of platinum carbon or iridium-based material, and you need to put it aside for any reason to coat your sample. So what is the shelf life? Do you have the same coatability? Do you have the same activity or not? So shelf life study also the things that after screening of the catalyst we are doing in our lab in order to make sure the catalyst is stay as good as the first day, or how many days we can keep the catalyst with the same activity and mass activity. The other work that we are running through the lab is that, as I told you regarding the platinum dissolution and detachment, we start producing shape catalyst. For example, here, as you see, cubic shape of platinum nanoparticle. So when you're, normally the platinum particle are circle, you know, and you don't have good attachment between your particle and your support. What we are doing, actually, we are producing shape catalyst, like hexagonal or like cubic shape, you know, in order to have a better connection between support and particle. This is one way. The other way also, we are working on the support material. For example, if you apply metal oxide support or support that has a better corrosion, anti-corrosion properties in compared to carbon material, it increases the durability of your catalyst layer. So here in this image, you see that we apply graphene sheet as a support for platinum, and we increase twice the durability of our MEA by using graphene as a support for our platinum. So it means that support plays an important role, shape of the catalyst play an important role in terms of durability. But if you want to play with the performance, then you need to talk about the size of particle. So it means that if you have a smaller particle, you will have a better performance. If you have a shaped catalyst and you have a better, for example, connection, you have better durability. Normally, bigger particle gives you better durability, but there is a trade-off. You know, you need to decide that there is a between performance and durability. You need to select that where you really want to stop, you know, to sacrifice the size in terms of the durability. So this is another work that is under publication that we recently published. So we actually try to build a alloy with the platinum and cobalt. And we did a lot of synthesis, and then this is the pole curve that recently we got it, and then it shows that with the almost half of the amount of platinum that we have inside the stack, we got almost the same polarization curve and same power density. So it means that one of the other ways that we can reduce the amount of platinum or precious metal or even iridium inside the catalyst layer is changing the support, having proper support in order to not to go through the corrosion. Second is that shaping this iridium or platinum particle or making alloy in order to reduce the amount of the platinum or iridium that we have inside the stack. There are a lot of research on catalyst available. There are a lot of research available on the literature, or you know, the many groups on working on catalyst. But less, you know, attention we see for the ionomer. However, ionomer has play an important role for making MEA, not in half cell, but also inside the MEA, inside the single cell and a stack. Actually, we did a lot of work on ionomer. I'm going to show some of that. So the state-of-the-art ionomer that we are using now is a PFSA, perfluorosulfonic acid. It's fluorine-based material. We have two ionomer, long side chain and short side chain, commercially available. So of course, it's a fluorine-based material. We are going to get rid of that soon, you know, finding other material that we are talking about, hydrocarbon-based material, but unfortunately, hydrocarbon is still, they don't have enough durability in compared to fluorine-based material. So now we are using a long side chain, short side chain, and the requirement for ionomer, they need to have good proton conductivity, they need to have a proper binding property, and also mechanically and chemically stable. Imagine that we select our catalyst through half cell, and we select our ionomer. I think that this is not, this is not my present. This is the first version of my presentation. I changed it. Yeah, so that's fine now. So I have one slide before that. So it shows that, for example, if we want to run the fuel cell stack or electrolyzer stack, we need to have a proper catalyst and proper ionomer. I will tell you why. So if we have a long side chain ionomer, it means that we have less sulfonic group in compared to carbon and fluorine that we have inside. What does it mean? It means that when we are making ink, we have less water retention. So now imagine that we are building a stack and we want to run that stack in fully humidified condition. Okay, so then in that case, we cannot use long side chain ionomer because we end up flooding soon inside the MEA. But if we want to have a stack and run it at dry condition, then our option is shorter side chain. Okay, it depends on the operational condition that we want to run our stack. We need to select the material. We cannot build the MEA and apply it for all conditions. It doesn't work like that. If we really want to get the best performance, best durability, we definitely need to select the material based on the operational condition. So now, imagine that you select your ionomer, you select your catalyst. The next step is that, how do you want to mix it? So mixing also is important. So that is a challenge that industry has, and also we have it in the lab, how we mix our catalyst in order to have a homogeneous ink and have better coatability and have that pores that I talked to you in, to have a better porosity for our catalyst layer. So here it shows, for example, this is the image that we apply different kind of ionomer. I show different SEM images that we applied shorter side chain ionomer and long side chain ionomer. You see that we will end up different porosity, agglomeration of the ionomer. And also this image shows that So this, we had the same catalyst, same ionomer, same method of mixing. The only thing that is different is a timing. And you see that when we coat the catalyst layer, we end up the homogeneous layer in one side and another catalyst layer full of cracks. So why? We don't need these cracks, because as soon as we start running our stack, the water goes through these cracks, start making wider and wider, and we have the lamination of our catalyst layer. So that is the reason that we need to pay attention to mixing method as well. So the other work that we did, actually, we applied short side chain ionomer and long side chain ionomer with different ratio to understand, okay, now we are talking, but if we have a commercial catalyst, you know, what ionomer is best for us and how we can figure it out under the same method of mixing. We understand that if you're using shorter side chain ionomer under high flow, that we make sure that we don't have flooding, you know, because when we have high flow of reactant, you know, all the flooding problem will be solved by itself. Then the catalyst ink that we are making is better with the shorter side chain ionomer. It means that we have better conductivity, better binding. But our performance is super sensitive to the longer side chain ionomer. So we talk about the role of ionomer on the performance, but do you think that ionomer also play a role on durability? The answer is yes. So it's not just the catalyst that we need to put a lot of platinum on the cell in order to have better durability, but also the type of the ionomer that we are using. So we did 30,000 cycle of MEA inside the 50 centimeter square cell based on the DOE script, and we found that, you know, the shorter side chain ionomer, it gives us a better performance in compared to longer side chain. Not only better performance, but also better durability. Then the other component that we have is a membrane. So membrane, like ionomer, the state-of-the-art material that we are using now is perfluorosulfonic acid. And we have, again, two types, like ionomer. We have longer side chain and shorter side chain. And recently, we see a lot of research on hydrocarbon-based material. Still, I didn't see good durability for hydrocarbon-based material, but I know that ionomer innovation working on that, and hopefully we see the progress on that as well. So basically, the role of membrane is that we need a membrane for transport proton from the anode and cathode, and it needs to be insulator for electron, and of course it separates the reactant. So like ionomer, it needs to have a good proton conductivity, good insulator of electron, and mechanically and chemically stable. So, we also do a lot of, you know, when we receive the membrane from industry, we do some ex situ tests before that we move forward through the in situ test for the to the stack, because our membrane, imagine that we have different components inside our fuel cell and electrolyzer. So if we have the material that they somehow accelerate the Fenton reaction, we may have accelerate the degradation of membrane inside the cell. It means that we have the pinhole, or we need to have a thinning of the membrane. So definitely we need to have the ex situ test before that we move forward if we are developing the ionomer. And then we have the membrane also, like catalyst layer, going through the degradation. So we have mechanical mode, thermal mode, and chemical mode. Sometimes we have completely delamination of catalyst layer from the membrane that increase ICR, or we have, as you see here, we have a pinhole inside the membrane, or on that image on top, yeah, here we have a membrane thinning. So membrane become thinner and thinner and thinner and increase the crossover. So then we don't have the good performance inside the cell. The other things that we did try in the lab is that, okay, now if we are using different membrane like ionomer, so what kind of operational condition is suitable for each type of membrane that we are selecting? So we find that if we are using shorter side chain ionomer, it is stand at higher temperature in compared to the long side chain ionomer. Or if we have low humidity, dry condition, because we need to preserve the water near three-phase boundary, it's better that we use shorter side chain ionomer in compared to long side chain ionomer. However, for electrolyzer, because we supply the water, then we don't have problem with proton conductivity. And so then on that case, we don't need water because we are supplying the reactant is water. Then longer side chain membrane and ionomer works better for electrolyzer. The other component that we have is gas diffusion layer. So basically, for fuel cell, anode side and cathode side, both we have a carbon-based material of gas diffusion layer. Inside the electrolyzer, just in the cathode side, we are using carbon-based material. And I will explain why and what is the anode side of electrolyzer. But here for gas diffusion layer, for fuel cell, we have two layers. Macroporous layer, that is basically carbon fiber and hydrophobic agent. And then we have microporous layer, that is our MPL plus hydrophobic agent. So if I want to talk about what exactly the gas diffusion layer doing for us, it somehow provide a support for our catalyst layer. It provides a flow path for reactant and also helping to remove the water, and also provide a flow path for electron and proton. Okay, so here I told you that we are using the carbon-based material in fuel cell, but we cannot use carbon-based material inside electrolyzer in the anode side. In the cathode side, we are fine. We can use the same GDL. But in the anode side, we need to use post-transport layer that is a titanium-based material. So why? Because we have higher voltage, we have different condition, and we have high voltage, and we have the more acidic environment. So the problem here is that the titania is the state-of-the-art material that we are using now. But if we use bare titania sheet as a PTL inside our electrolyzer, we will end up the passivation layer. So we will grow passivation layer, and this increase the interfacial contact resistance, or ICR. So definitely we need the coating. What is the coating now that people are using, or industry is using, or the state-of-the-art is platinum. So it means that we have platinum-coated PTL for electrolyzer. So another part that we need precious metal for electrolyzer. If you remember, for fuel cell, we just apply precious metal for catalyst layer. But here now you see that we have precious metal on PTL as well. So one of the work that we are doing in my group is that actually we have two big projects on that, how we can replace this platinum with other metal. Okay, because the PTL that we are using now for electrolyzer, it's not developed for electrolyzer. It's developed for other application. So we are taking that and we are applying inside the stack. Because until now, we didn't pay attention that much for hydrogen production. But nowadays, people start looking at that and, develop the material and PTL and novel coating in order to bring down the cost of electrolyzer. So as you see here, that we see that we have the gas diffusion layer making of carbon nanofiber, MPL making carbon-based material, and then we have a catalyst support that is making from carbon-based material. A lot of carbon, yeah? So we want to be carbon-free, but a lot of carbon-based material inside fuel cell. So one other work that we are doing in my research group is that how we can replace this petroleum-based material with bio-based material. So these are the carbon material that we provided in the lab, and we are applying through the MPL, through the catalyst, and we got a good result. Hopefully you see it's under publication. You see the results soon. So this is also one of the interesting results that we published back 2019. So we applied graphene and carbon-based material for MPL. We somehow optimized the amount of ionomer, type of ionomer, how to build the catalyst layer all together, okay? And then we end up with the MEA that is not sensitive to the flow. For the people that they are in the field, they understand that. What does it mean? It means that you produce the MEA that if you have high flow, low flow, or moderate flow, you will end up the same performance. It means that you will have a perfect porosity in place. When you run it, you have enough reactant to run your fuel cell. So the conclusion is that if you know what operational condition you want to run your stack, then it's easy to build the MEA, proper MEA for your purpose. And then, okay, so now we talk about the type of material that we have. We talk about the type of, for example, the state-of-the-art catalyst, type of ionomer, membrane. So now how we make the MEA. Normally we have three methods for making our MEA. We have catalyst-coated substrate, we have decal method, and we have CCM method. So catalyst-coated substrate, when we are making the ink and deposit our ink on our GDL directly, so it's easy without any problem, very easy. However, the majority of our catalyst, it's gonna sink inside the porous. So this method is perfectly fine if you have high loading. If you have high loading of catalyst, then it's easy to produce CCS. But if you want to bring down the loading of catalyst, then we may think about CCM or decal method. CCM is the one when we are transferring the catalyst ink directly to the membrane. So what is the problem? Because of the texture of the membrane, when we are putting the ink inside the membrane swells and or shrink or desize. So we need to figure it out the way that deposit the catalyst layer on top of the membrane without the shaping of our membrane. So in order to this method be easier for industry select decal method. What does it mean? They are putting their catalyst layer on the inert substrate that normally is Teflon and then transfer it to the membrane. So that is going through the roll-to-roll machine. So also we did actually try a lot for the CCM, decal CCS, to understand which method is best for making MEA. So we found that if you have high catalyst loading, for example, for fuel cell, if you have 0.4 milligrams per centimeter square platinum inside the cathode, no matter if you use CCM, CCS, or decal, you will end up the same performance. Okay. The problem is when you bring down the coating loading. When you have low loading of the platinum or iridium inside your catalyst, you cannot use CCS, because the majority of your catalyst is going to sink inside the porosity of your GDL or PTL. So definitely then you need to consider either CCM or decal method. So all of this research, won't happen without my team. So thank you so much for listening to me. And thank you. And it was not my slide. Actually, it was the first version of my slide. I sent the second version. So thank you so much. I don't know what time. I don't have a time in front of me. But I will be happy to get questions if you guys have any. Sorry, it was too technical, or I just try because I know that different people talk about different methods of producing hydrogen. I wanted to take you inside the stack to see that what kind of challenges we have and what is the direction of our research group. So for fuel cell, we don't need to do that because we have a DOE. So DOE for all the component has the accelerating stress test in place. They did a lot of research. They work with the different big lab in the world, and they already made the accelerating stress test for component. Inside the fuel cell, if you want, nowadays, if you want to stress your membrane or if you want to stress your catalyst, even platinum or carbon or even ionomer, we have a perfect script there, the well documented, everyone can use it. Now the problem is electrolyzer. We don't have accelerating stress test for electrolyzer. So if your question is for electrolyzer, yes, we have 2 projects actually with National Research Canada that we are building the accelerating stress test for the electrolyzer for different components. That is not in place, but I hope that it comes soon as well, something that everyone can use, and then we can compare the results together. Because now for electrolyzer, all the lab, they have their own accelerating stress test, and sometimes the result is not comparable with each other. Yeah, but for fuel cell, we are okay.
You mentioned that we can consider different MEA for fuel cell depending on the application. Will this have an impact on the cost of the fuel cell?
Of course, yeah.
Is it that significant?
Of course. For example, sometimes you don't need a durability. You just want to run it for a couple of hours. Then we don't need to apply platinum, precious metal. So the cost is substantially, decreased. But sometimes you need a really durable. So even, for example, for selecting bipolar plates, you know, the volume of fuel cell is not important for us. We prefer to have graphite-based bipolar plate rather than metallic one. But if you're talking about auto application, then the size is important for us and weight is important. Then we need to consider the component that is lighter and take less space. So we are going through the, for example, metallic-based bipolar plate. But if we are talking about metallic bipolar plate, like electrolyzer, then we cannot apply, for example, stainless steel, bare stainless steel inside the fuel cell stack, because as soon as you put your stainless steel, it starts corroded and iron will be free, and then you accelerate the Fenton reaction, you will produce the hydrogen peroxide, and you have a big pinhole inside your membrane. So that's the problem. So you need to have a coating for that. Again, the application is really important in order to select your component. Yeah.
So if we have different components for different application, it will mean that the cost of each component will not decrease by mass production.
Of course, yeah.
And it will
definitely
still be high.
Yeah. So hopefully, you know, my hope is that, you know, actually my dream is that we can make all of these components here in-house in Canada. So we don't go and purchase all the components from this country or that country. So I hope that one day we can build all of, and we have all the capacity, you know, we have the mineral, we have the technology, we have the resources. So hopefully, I hope that we can build all these components inside and then develop the stack based on the application that we want to run. Yeah.
Thank you.
Anytime. Yeah. Okay, guys, thank you so much again for listening.